So welcome back. Okay. Now today I've just listed as to how I'll go. There is no need to tell you about the electric field. I have talked to you about flux in and flux out. We'll talk to you about dipole, and we'll calculate the electric field due to a dipole on the axis of the dipole, okay, and on its equatorial axis. Then I will briefly talk to you about the physical significance of dipoles, and probably when I end up, okay, then the dipole in uniform external electric field. And continuing with that, I will talk about continuous distribution of charges, okay, and introduce to you Gauss law. Maybe not today, everything about it, because I want to introduce to you flux in and flux out very easy. Now, I just want you to recall about the dot product of two vectors a and b, ab cos of theta, okay, and a dot b is equal to b dot a cross b. If there are two vectors, then we get a new vector c such that c dot a or a dot c, they are equal and equal to 0, c dot b and b dot c, they are also equal and equal to 0. That means the vector c makes an angle of 90 degrees or pi by 2 with a and also with b, okay, and c cap is either out of the board or into the board, so that a cross b is equal to minus b cross a. After that, I just give you a reminder here as to what is a surface. A surface is definitely a vector, but we don't define this as a vector as it is. But I told you that if I am able to define a vector and multiply that vector by a scalar, I obtain a new vector. Divide it by a scalar, I get a new vector. For example, vector p is equal to m into vector v, and vector v is equal to vector p divided by m, etc., etc. Please recall that. Here I have just taken a rectangular set of two vectors x and y. They are all space vectors x and y. Now, I told you that in the cross product of two vectors, a cross b is equal to c. So here, what we do in that situation is take my right hand, take your right hand with the fingers, the curl of the fingers, the natural curl of the fingers. What we do, we rotate x towards y. Then what is obtained is this kind of a parallelogram, which is a rectangle in this case, and this gives us the area of this parallelogram is proportional to the vector magnitude of vector c. So the magnitude of the vector c is equal to ab sine of theta. Theta in this case is pi by 2 radians, which is sine of this is equal to 1. So I'll get the area that we obtain over here will be equal to x multiplied by y, okay, into sine of 90 degrees. So or pi by 2 radians, and s cap. S cap in this case will be shown by your thumb, my thumb, anybody's thumb, and it is out of the board. Well, if we do otherwise, we do y cross x like this, then you can see that the thumb will go inside, and that is the direction of the new vector. Okay. Here, s is out of the board. Now, like I asked you before, I am going to ask you again. One page, please. Give me one page. One page, please. And you'll find that you can never give me one page because if you give me a page, there are two sides of the page, and therefore you can never give me a page, like you can never give me a monopole of magnet, etc. And what you can give me is a leaf of paper, which is called panna in Urdu or in Hindi, Hindustani. Okay. So you can give me a leaf. You understand now that every surface has two faces. One is this face, its vector is towards you. And there is another face for which the vector is in the other side. The vectors are normal to the surface. Okay. So I can show you that in this case, now I am taking you through a surface. Often, instead of the cat vector, we take the normal vector. So here I am having again a surface like this, for which this is the normal vector in this direction, and for this surface the other side normal vector is in the other direction. So I have shown one as n cap and the other is minus n cap. No problem. Now let us take a set of electric fields parallel to each other and equidistant. That means it is a uniform electric field. Okay. And here I keep the lines of field are parallel to this edge, and if I keep it here, then how many lines of field will pass through this surface or this surface? The answer is 0. Okay. So in either case it will be equal to 0. Right? Well, E dot ds will be equal to E ds cos of pi by 2, where pi by 2 is the angle that it will make, and therefore plus pi by 2 or minus pi by 2, it doesn't matter. In both cases it will be equal to 0. So there is no flux in, there is no flux out. Now please look here. Look here. I have shown some dots, another set of dots, another set of dots, another set of dots, 4, 4, 4, 4. So that makes 16 dots. Okay? In the row or in the column, the dots are equidistant, which means that there is a uniform electric field which is coming out of the board. Now if I keep a surface here, just like that, and this surface is, the ds1 vector is out of it. So if I put my surface over here, then my surface has a vector which is coming out like this. In that case, what is the angle between the two? E and ds, the angle between the two is 0. Okay? And if we talk about the other side, okay, other side, then it is going out, the ds vector, ds2 which I have shown here, and the angle again between the two of them is 180 degrees or pi radians. So this is what I am writing here. E ds1 is equal to E ds1 cos of 0, y right degrees 0. Okay, E ds1. This is when the flux is out. And for the surface ds2, E ds2 cos of pi, and cos of pi is equal to minus 1. So then in that case we say that the flux is in. Okay, so if I have, go to that city, अरे बैठने वाली यार. So if there is a flux, for example, there is a bulb here and the light is coming, and the light is coming into this surface. So there is a fluxing on this side of the surface, and there, flux in and there is a flux out. Okay, so flux in and flux out has to be understood by you. Okay, and this is exactly what we'll do in the due course of time. Now next we take up an electric dipole. So we have had this, and this is out. Now dipole. Dipole. Before these electric dipoles, we had magnetic dipoles. Pole is an extreme, what we call in Hindi dhruv, and North Pole, South Pole, Qutub, Qutub, just like Qutub Minar, Qutub Shumal, Qutub Junub in Urdu. But here I have two charges, negative Q and positive, and they are separated from each other on the line joining the two, which has been shown with the broken line by, this is the center of the dipole. A plus A is the distance separation between the two of them, which is equal to 2A. Well, the dipole is assigned a dipole moment, which is a vector. The vector which points from the negative Q to the positive Q, okay, from minus Q to plus Q. And the magnitude of this P is equal to the separation between the two charges multiplied with the value of one charges. And of course you have to bear in mind that the direction is, P cap is like this, the cap vector is like this. Okay. This line joining the two charges has been extended on this side and also on this side by a continuous line. And this line, which passes through the center of the dipole and the two charges, is called the dipole axis. The dipole axis, which is a single line. Then what I have shown you here is a line which furcates this line at right angles. It is normal to the axis of the dipole. This dipole axis is a single line joining 2 points, but the equatorial axis is not. Because, look here, if I have a dipole which is towards you, okay, or I have a dipole which is away from you, the P is pointing towards us, towards you, and the P is pointing away from you, then that means it is perpendicular to the board. And in the board I have just shown, it need not be confined, but what I mean is that if I draw any line, for example like this, continued in the opposite direction, okay, then this line is perpendicular to the P, that is the axis of the dipole. How many lines you can draw from here on this plane? The answer is umpteen, infinite number of lines. So these are the lines which decide what is the equatorial axis. So this becomes, the board becomes, okay, the whole board becomes the equatorial plane, equatorial axis and equatorial plane. So anywhere on the equatorial plane we can make calculations for the electric field, okay. Now, while this was done for a long time during the days of, even after that, when the small bar magnets were taken and we had the compass needle, we used to draw lines of force. In fact, lines of field. Okay. So Faraday's times, the single line dipole axis was also known as long side on. A point on the long side on. And for this one, the equatorial axis, there is another term that was used, was called broad side on position. Okay. So now I finish with the dipoles and I go for the physical significance of dipoles, which also I finish in a couple of sentences. In fact, what is there in nature? We have natural molecules. The molecule comprise often two or more atoms, and these atoms have charges in their nuclei and charges on the clouds outside the nuclei with which they are interacting. A lot of forces, this, that, everything is there. So if we just freeze that molecule at any moment of time, then what happens is that the center of the positive charges and the center of the negative charges, they are in natural molecules, certain natural molecules, they are separated by a distance. Okay. Now suppose if it is not natural and the center of mass of the positive and the negative charges is at the same position. If this system is kept in an electric field, what happens is that the center of mass of the positive charges, this will shift towards the negative polarity, and the center of mass of the negative charges, that also shifts like this, so that there becomes a separation. So this is called an induced dipole. So dipoles can be natural, dipoles can be even there are things which are known as quadrupoles, which when the occasion comes I'll talk to you about. But now I am going to do is to calculate the electric field on the dipole axis and to calculate the electric field on the equatorial axis or on the equatorial plane. So on the dipole axis or the axis of the dipole or on the long side on position, I take a dipole here minus q and plus q here, so that P is equal to 2aq. As it is, the direction is minus q to plus q, I always remember, and I am just taking point P over here. Okay, the point is P on the axis of the dipole, on the right hand side, on this side. Now what will happen? The field due to this positive charge will be more as compared to the field due to the negative charge, which will be an attractive field. So the electric field, the direction of the electric field, resultant electric field will again be in this direction. This is also the direction of the vector P, which I have not shown here. Suppose I take the point over here, okay, then what happens? It is closer to this, but the electric field content over here due to the negative charge is more as compared to the pushing electric field content due to the positive charge, and therefore once again the net direction will be like this. Okay. Now always remember that the distance of this point from the center of the dipole is normally much larger, x is much larger as compared to A. Okay. Is rather much more large as compared to A. So with this sketching that I have done, I have these two contents, E plus, which is larger than E minus. I am not taking the directions, I have just shown you the directions, I am taking the magnitudes, and I say that the net electric field therefore will be equal to the larger content minus the smaller content, which turns out to be like this. Okay. We also find that E cap, that is the direction of the vector, calculated electric field is parallel to the dipole moment vector, which is from the negative charge to the positive charge. Okay. So let me now calculate and write the value of E plus 1 upon 4 pi epsilon naught Q upon x minus A, because this separation over here is equal to x minus A. This is x and then minus the A part and x minus A, that we get over here whole square. E minus 1 upon 4 pi epsilon naught Q upon x plus A whole square. So the value of E I can write as Q upon 1 upon 4 pi epsilon naught into Q, and in the brackets what I have is 1 upon x minus A whole square minus 1 over x plus A whole square. Okay, and if I just take the LCM here, then I'll get x square plus A square whole square, and here I'll get x square plus 2xa plus A square minus x square plus 2xa minus A square, so x square, A square, they cancel, and finally I get 2xa divided by this quantity. Okay, which I can write 4xa, 4a into q, I can write as 2p. Okay, then I get it here, x here, and 4 pi epsilon naught x square minus A square whole square, and which I write here again so that I can cancel one of the x, because first of all I'll say that x is very, very large as compared to A, so this is negligibly small. Okay, and I can write this as an approximation, and I get a value like this under the condition that x is very, very large as compared to A. So finally friends, so this 1x cancels, and here I'll get x cubed. Okay, so the value of the electric field that we calculate in the dipole axis of the left hand, I'm sorry, not left, but long side on position, okay, that turns out to be 2p upon 4 pi epsilon naught x cubed. Okay. Now to you it appears that 2 has been emphasized. Okay, yes, and yes. This 2 has been emphasized because what we will obtain in the broadside on position, there will be something like this: p upon 4 pi epsilon naught y cubed, if this direction is taken as y, or otherwise we can write both of them as r. So p over there in the equatorial axis and 2p here on this axis, and there I will find another thing. The another thing is that the electric field will now be, instead of being parallel to the p vector, instead it will be rather anti-parallel. It's in the opposite direction. So it means that I can say that 2p constant, 4 pi epsilon naught constant, so this whole thing is a constant, so I can write that the electric field on the dipole axis on the left, left, okay, long side on position is proportional to 1 over x cubed. What did we find in the case of a single charge? This proportionality was 1 upon x square. That means the fall is faster much faster as compared to in the case of a single charge. I will compare this value with the electric field on the equatorial axis, which we call the broadside on position. That comparison and this discussion will follow in the next lecture, and that way I have done electric dipole field on the axis. So we are left with equatorial axis and then the dipole putting a uniform electric field, Gauss law, etc., etc. Thank you very much. See you again.